Hey all, welcome to the fifth video for the CSES problem analysis programming. So the question name is removing digit, and it is a pretty straightforward question, and even it would work with greedy as well. And so if you haven't read the problem statement yet, please pause the video and go ahead and read it and try to solve it yourself. And so now we will be discussing. So you have been given an integer n. On each step, you may subtract from it any one digit number that appears in it, and you have to do it until n becomes 0. For example, we have 27 here. I can remove 7 or 2 from 27 to get 25 with 20 or 25. And then I would again repeat the process for 20 and 25. So if we see, then we can see that 27 can be broken to 25 and 25, 5 and 20. 25 can be further broken to 20 or 23. As we know that 20 is already here, so we don't need to consider it again here. Just for the dry run, right? It's just for explanation purpose. So 20 can be broken to 18 only. 18 can be broken to 10 or 17. 10 can be broken further to 9, and 17 can be broken to 10. 10 would be further broken to 9, and 9 would be broken to 0. And well, you can see we can read 0 here in less number of steps, so we don't consider this. Right? And now for the 20 part, we can reach 20 here in one less than one, right? So we don't consider 20. In 23, we can reach 20 here, or we can reach 21 as well. As you can see that 20 would also already lead to a bigger, we can already reach 20 with less number of cents than this. We don't consider 20. 21 can again be broken into 20 or 19 because we don't again use 20. And so on and so forth. As you can see that it would get to 10, then 9, and then 0. Right? We can see that these require less number. So 27 to 21 moves, 20 to 18 second, third, fourth, fifth. It requires a total of 5 moves. The output is 5. So as you can see, a greedy approach works here. You just remove the larger one, and it would always work. So why greedy approach would always work? This is because there is no valid number or valid pair in which valid pair A B such that A is greater than B and A requires less number. This is not there is not any case in which this statement holds. No case for this statement. So if this statement does not hold, that means the greedy approach would always work. If I go less, then I am always right. So also, yeah. So this is the pretty much it. So the a greedy approach might would work here, but we would still be using DP for it because it is a part of dynamic programming field. Okay, so there's no other reason for it. Right? You can use a greedy approach, but DP approach is also like a greedy approach. I'm just storing the results. That's the difference. All right. So what I would be doing is just would be creating an DPI, and for each DPI would store the minimum operations needed to turn I into 0, as you have guessed, right? And what would be my recurrence relation here? Recurrence relation would be simple. Now DPI would be equal to minimum of DPI and the current number. and the current basically either I would remove that specific digit or I would not, right? So dpi minus hc. So for example, suppose I have a number called num as 27, and I iterate over 27 with a j loop, right? And either I would consider the specific digit or I would not consider the specific digit, right? So these two cases in which I do not consider it and in which I consider it, right? So we have to initialize all our dp with infinity because we are taking minimum of that, and dp 0 is equal to 0, right? Because I don't need any number of operations to turn 0 into 0. So this is the code. I initialize it with infinity. For me, infinity is 10 power 9. Alright, you can have 10 power 18 as well. So for int I is equal to 1, I less than n plus 1, I plus plus. I just iterate from 1 to n, and then I iterate to iterate to the given index I, and the given index, because the given index tells us the current x we are at, right? The dpi, this I, we have to iterate over the digits of this I. So with this loop, I iterate over the digits of this I after creating it to a string. And dpi is equal to minimum of dpi minus sj minus 0 plus 1, right? And you have, oh sorry, I forgot a plus 1 here because number of operations plus 1. I operated once more, so it would be plus 1 here, right? And I would just see out dpn. The answer would be dp stored in dpn because of the state, right? The state was minimum, maybe to turn n into 0, right? So I guess it was simple, fairly simple. You could have used greedy as well. It would give you an AC, I guess. And I haven't solved it with greedy. I would, and I would encourage you to solve it with greedy as well. So let's see if I solve it with greedy or not. But this solution is a pretty straightforward solution for a difficult solution, right? So I guess was easy. The overall time complexity of the solution is order of n. Now the this loop would be the number of digits, and the number of digits is log n, right? Approximately log n. So the total time complexity would be order of n log n, and the page complexity is order of n, as we can see. So that is it for this question. Let's see the next question, the spoiler for the next question. And it's a very trivial question actually, and very simple basic DP here. I mean, it is not even DP if you consider it. Okay, it is simple, very simple DP, right? So try it yourself, and just a little hint that you can move to this position from your up or right? So consider this, and let's see if you are able to. If you are not, I'm there for you, right? So till then, bye bye.